In today's lesson, we'll be talking about rational functions. This is one of two lessons that we are going to have on rational functions. Today's lesson is just an introduction and a refresher, and we'll be looking at more simple rational functions, whereas the next lesson, you'll start to look at more advanced functions as well as features, like wholes, for example, and oblique asymptotes. At the end of today's lesson, you will be able to find the domain, state the asymptotes, and graph simple rational functions using transformations. Let's look at what a rational function is again. It is in this form where p and q are both polynomial functions. The domain consists of all real numbers except anything which causes the denominator to be 0. Remember, we can't divide by 0 or we have an undefined function. Let's start off by reviewing the domain with these functions. So remember, we can't have any x value that would cause our denominator to equal 0. So let's look at this first function. This is a rational function. In order to make that determination, we have to factor the denominator. It factors into x plus 6 and x plus 2. So we have two numbers that could cause the denominator to equal 0. And that would be a negative 6 or a negative 2. So all real numbers are in the domain except for negative 6 and negative 2. How about this second equation? Well, if you'll notice, we have x minus 4 and x plus 4. So the two numbers that would cause the denominator to become 0 would be negative 4 and positive 4. Now you're probably wondering, why don't we simplify and cross off x minus 4? Well, we can do that, and we'll do that in our next lesson, but there are some consequences for doing that. And one is that you do not see all the numbers or values that cause the denominator to equal 0. So you always need to find your domain prior to simplifying. That's really important. So let's make a note of that. So now jot this down. Always find the domain prior to simplifying, and that's going to be very important in our second lesson. Look at the last problem. What would cause this to be 0? Well, you might think, oh, negative 9, but negative 9 squared is a positive 81. Can you plug any number in here that would cause this value to turn into negative 9? And the answer is no, because if you solve this for x, you end up with an imaginary or complex number. Therefore, in this case, all real numbers work, and we don't have any domain restrictions. Let's review our asymptotes. Think about our horizontal asymptote. If, as x approaches infinity, so if we head towards positive infinity, or if, as x approaches negative infinity, in this second example, the values of our function, in this case it's r, approach some fixed number L. So if you'll notice end behavior, that's where asymptotes play a part in guiding our end behavior. So this end behavior here is going to come down and get really, really close to this value L, whatever that may be, 2 or 1, but it will never cross it or touch it. Same thing up here. This value of r is getting very, very close to this value of L, or I should say this function r is getting very close to this value of L, but it will never cross it or touch it. That's this end behavior. And this forms our horizontal asymptote. Let's look at our vertical asymptotes. It's the same concept, if you remember. If as x approaches some number c, the values as we go to infinity, then the line x equals c is a vertical asymptote of the graph of r. In other words, as our end behavior travels up towards positive infinity, our value that we approach for x becomes some constant value c. Maybe this is x equals 3 or x equals 4. And this can happen at any end anywhere. Notice that in this first example, this end's getting very close, and over here, this leg, this end is getting very close. Here's another way that can happen as well. Finally, let's explore oblique asymptotes. We're not going to be calculating that in this lesson, but we will in the next lesson. Notice that an oblique asymptote is really just a linear function with a slope. So if an asymptote is neither horizontal nor vertical, it is then called oblique. And this end behavior is coming out to the right and up, and it's getting very close to this oblique asymptote, but it will never again cross it. Now this end is not following this oblique asymptote, but perhaps it's following something else, or it's not going to follow an asymptote. Let's go ahead and practice finding vertical asymptotes. So here we have a rational function. It's been factored. What are the vertical asymptotes? Remember that the vertical asymptotes are very close to the domain. We find them by examining our denominator. The vertical asymptotes are going to be values that our function can never be. Remember, that would cause it to be undefined. That's why we have an asymptote. So in this first example, you should have said -1 and +1. So we would have two vertical asymptotes because neither one of those values will work. What about the second one? Well, in this case, remember, if we subtract 1 and take the square root, we have an imaginary number, so we don't have any limitations on this. So we have no vertical asymptotes for this first one. How about this second one? Or this third one, I should say. In this last one, if you'll notice, x minus 3 and x minus 3 were canceled. That's okay when we're finding asymptotes, but it's not okay if we're trying to find the domain. So in this function, we would only have one vertical asymptote, and that would be at x equals -4. Let's now practice finding horizontal asymptotes of the graph. For this, we are just looking, like I said, at these very simple rational functions. We won't have a full polynomial in our numerator for these. In this first case, this is actually our parent function. The horizontal asymptote is always going to be showed off to the right, if you remember. So in the first case, since there's nothing there, our horizontal asymptote will be at y equals 0. In our second case, we have a 3, so our asymptote becomes y equals 3. Can you guess this last one? You are right if you said y equals -4. So this all brings us around to transformations. And what does all this look like? Well, here is our simple rational function. Notice that A represents our vertical stretch. Our H here is our horizontal shift left and right, and the K is our vertical shift up and down. Here again is our parent function, and you can see that on the parent function we have no transformations. We have no -h, and we have no +k. Therefore, we have x equals 0 and y equals 0 as our two asymptotes. Notice our legs. We have our two legs. So when we're graphing rational functions, we always want to consider the fact that we have more than one leg. When we're creating points from our simple rational function, we are going to need two sets of points, one for each leg. So with our first leg, we're going to start off on the positive quadrant. We'll start off with a 1, and let's do a 2 and a 3. For this leg, we'll start off in the negative quadrant with -1, -2, and -3. In this case, 1 divided by 1 is just 1, and therefore we have this key point here. We talked about in the last lesson a vertex compared to a reference point. So in this case, this is a reference point. If we plug in a 2, we get 1/2, and then a 3, we get 1/3. On this angle, it's the same thing, only negative. So those are our reference points for our parent functions, and you can see here's our main reference point right here. So let's go ahead and look at some more transformations, and we'll graph. So here we have a function, y equals 2 over x minus 4 plus 1. We're going to graph this, and then we're going to state the domain, determine the asymptotes, and state the transformations. So let's do this out of order a little bit. Let's think about our transformations. First thing is the 2. So we have, number 1, a stretch of 2. Then you can see there's this -4 on the end here. So we have a shift. And remember, we shift the opposite way, so we are going to shift right 4, and then this 1 on the end means we're going to shift up. We have a vertical shift up of 1. In order to graph these then, remember we need our two tables, one for each leg. So we'll make them a little bit far apart here. And then in our first table, remember that we started off with -1, -2, -3. And then our positive leg, we'll start off with 1, 2, and 3. These are our parent functions, remember, -1, -1/2, -1/3, +1, 1/2, and 1/3. So that's our parent function. When we transform this, we need to think about our transformations. We have a stretch of 2. So that means that we are going to multiply our y components by 2. Let's fix that a little. And we are also going to have a +1, which shifts us up by 1. So we would put that on the end. And now let's consider our x. For the x, we're shifting right 4, so we know we need to add 4 to both these legs. Let's go ahead and do the math and see what we come up with. So in the first one, we would have a 5, a 6, and a 7. Over here, 2 times 1 is 2, plus 1 is 3. 2 times 1/2 is 1, plus 1 is 2. 2/3 plus 1 is 1 and 2/3. Over here, on this side then, -1 plus 4 will give us 3, 2, and 1. And then over here, -2 plus 1 is -1. This becomes -1 plus 1 is 0. And -2/3 plus 1 is +1/3. Now that I have my points, I can plot those like I did here, but it's very hard to determine how my end should go. Should it go up? Should it come across? So one of the most important parts of graphing rational functions is to determine your asymptotes and plot those first. So, what's our first asymptote? Well, if we look here in the bottom, x minus 4, we know that we have an asymptote at x equals 4. If I go to x equals 4 and draw a line for my asymptote, that will help to guide my end behavior. So what's my other asymptote? Well, I have this +1 on the end here, so I know that I'm going to have a horizontal asymptote at y equals 1. So now I'm going to where y equals 1, and I will draw in my second asymptote here. Now I'm in a much better position to fill in my graph. So these points are going to form a curve, and the ends will come up very close to these asymptotes, but again, never cross them or never touch them. I'm getting as close as I can. So now I have graphed, I have determined the asymptotes, I have stated my transformations. What is my domain? Well, my domain really is just what x turns my denominator into 0, and that is 4. So in this case, it is all real numbers with the exception of 4. In interval notation, that would look like this. Or you can say that x does not equal 4 if you want to write it in algebraic notation. And this is how you graph simple rational functions. So now at the end of this lesson, you know how to find the domain. You're able to state the asymptotes as well as find them, and you can graph these functions using transformations. Our second lesson, we will start to use more complex rational functions and apply some rules for our asymptotes as well as find the oblique asymptote.